suppose output is a function of K and L. And let this be an aggregate production function for an economy. An economy's aggregate output depends on how much capital is used, how much labor is used. And we're going to study economic growth. We're going to study how output changes over time. So over time, the capital stock will change. People will save. The savings will go into investment. It'll cause the capital stock to change over time. So let's just let this function be K of T. This expression right here, instead of calling it F of T or G of T or H of T, let's just call it K of T. And it's understood capital here is a function of time. And we'll do the same thing for labor. Labor force will be a function of time. Perhaps just because of population growth over time, the labor force will grow. Okay. The labor force could also grow if more people decide to work, if there's an increase in labor force participation. But as a simple explanation, you could just think of this as due to population growth. Population grows over time. Question?
Why use the K there?
Okay. It's just a notation that is kind of convenient and is often used. It would be all right, David. We're using F here. You could call this G of T, and you could call this H of T. But sometimes, since it's capital, they just write K parentheses T. And it's understood, David, that means capital is a function of time. It's just notation. Actually, it's kind of simplifying notation in a way, because if we used K equals G of T, then you have to think, oh, K and G are really the same thing. But now you don't have to, because you just put a K instead of a G. Okay. So since K is a function of time and L is a function of time, notice that output can also be expressed as a function of time. Okay, if I just substitute in here F of K, but K is a function of time, L is a function of time. So ultimately, output is going to be a function of T. And we can get the total derivative of output with respect to time. It's very easy. And again, let's just start with dq. And since you all know this by now, dq is just partial q, partial t, partial q, partial k, dk, plus a partial q, partial L, dl. So we'll just start with that. Notice q is a function of k and L. In this case, Diana, notice t doesn't appear in the f function. So in this case, there'll be just two indirect effects of time on output. So in order to get dq dt, all we have to do is very simply divide both sides of this expression by dt. And now this thing right here is the total derivative output with respect to time. I'll just say total derivative. It's obvious it's a total derivative of q with respect to t, because dq is in the numerator, dt is down here. That's the total derivative. And these are two indirect effects. Now you got two indirect effects. Both of these are indirect effects of time on output. This one shows the effect of time on k, and in turn the effect of k on q. This indirect effect shows the effect of t on L and the effect of L on q. So both of these are indirect effects. but this would be called the total derivative of output with respect to time. There's two components. As time changes, K changes and L changes. So you're going to have two indirect effects of T on Q. Okay. All right. Does that make sense to you? Okay. Oh, let's draw the channel map for this problem. The channel map for this problem would look like this. Here, our ultimate disturbance is T. When T changes, that causes K to change. Capital accumulates over time because of savings and then investment. And when K changes, that affects Q. So that's one indirect effect. The other indirect effect is this. As T changes, L changes. As L changes, Q changes. So in this particular model, you have two indirect effects of time on output, but no direct effect. Yes?
How would it change if T within the function?
Oh, in the F function?
Yes.
Very good. That's an excellent question, Jessica. Let's do that. That will be a different model. But it actually is a model that is commonly used. So let's look at that. So now let's just replace it with this. Q is a function of T, comma K, comma L. Now T is in this F function. Again, it's obvious that Q could be expressed as a function of time because you've got T in here, then you've got K, but K itself is a function of time, and L is a function of time. So now if you want the total derivative of Q with respect to time, I would suggest you do it this way. Start off with the total differential, dq. And dq is just going to be partial Q, partial T dt, plus a partial Q, partial K dk, plus partial Q, partial L dl. That would be the total differential. Notice now there are three components because you got three variables in here. Okay. So, but that's the total differential of output. Now, if you want dq dt, Jessica, just divide both sides of this equation by dt. And you get dq dt equals a partial q, partial t. dt over dt is 1. Plus partial q, partial k times dk dt plus partial q, partial L dl dt. Okay. Now, this term right here, Jessica, is the direct effect. This is the indirect effect, same one we had before. And this is the indirect effect, too. Exactly right. Exactly right. I'm so proud of you people today. You're really tying this stuff together. You're asking good questions. Yes, the only difference, this channel map, there would also be a direct effect right there. So this would be the direct effect. This would be an indirect effect. And this is an indirect effect. And by the way, this model right here, Jessica, is the model that was used by Robert Solow in his study of economic growth in the U.S. I think he wrote this paper in 57, something, a study of economic growth in the U.S. This is the framework he used. And now time represented the state of technology. Over time, firms use better technology. And what that means is for any given values of K and L, you get more output just because of the technology's improving. Over time, K increases and L increases. And so Solow used this type of model as a framework for studying economic growth in the U.S. And his work was very influential. And that's in large part why he won the Nobel Prize in economics 15, 20 years ago, is by using a model just like this to study the determinants of economic growth. He not only had a theoretical model, but then he empirically estimated it using data and won the Nobel Prize. He used a model just like this.